Ho 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 ho! Hello, hello! Merry Christmas season! How's everyone doing? This is Jose Luis here at Parametric Camp, and welcome to the second video in this mini series where we are creating parametric tools and computational tools to illuminate a Christmas tree that has been wrapped with a string of 500 LED lights that can be individually addressable and controlled in their RGB colors. Whoa, 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 whoa. I'm gonna take this because it's gonna fall and it's gonna break. Can you see how this is? This was green. So in the previous video in this series, I showed you how to create a simulation framework. So taking the coordinates of the points from a file and taking some animations that have been generated as a CSV file and do some custom rendering with Grasshopper. In this video, I would actually like to get hands-on into the actual generation and the design of those sequences of illuminations and generating those CSV files that we will be able to then load on the Christmas tree. So what you can see is a few examples where, for example, I have generated a CSV file that has absolutely nothing, and that's what I'm seeing here right now, that is useful for turning the LED tree off, and actually we will be using that a lot. Or for example, I can generate a sequence where the tree just pulses all the LED lights, turn on and turn off very slowly, just pulsing in unison, all right? That is not very exciting, but it's a good segue into figuring out how these sequences can be generated. We can do absolute random, so we can just generate a blinky effect all together randomly on the Christmas tree. We can do that in monochrome, or we can do that with color. It's equally easy or difficult. I've actually run this in the real world and it's not very nice to watch it. I'm much more into the mood of more, let's say, minimalistic approaches or delicate approaches where if we're going to do random, let's just do it in a small, soothing way. I'm not sure if you can appreciate how the LEDs are very slowly fading in and out, but at a random offset from each other, but in a very soothing way. I like this a lot. Or if you want to go more on a Christmassy kind of way, you can take a look at doing this, but with two sets of random colors, green and red, for example, just for more of like a Christmas flavor kind of situation. And last but not least, we can also have that random offset applied along the elements of the string of LED lights. Because the LEDs are placed one after the other in a string, it's very easy to know their position along the wire, and therefore make the offset be slightly off along this wire. And therefore, because all the LEDs are very physically close to each other on the tree, it will generate this spatial effect of the light traveling up and down the tree, which is very interesting. This is not taking into consideration where the LEDs are in XYZ. It's just a consequence of the fact that the LEDs are actually very close to each other in physical space. All right. So the examples that I'm going to run into, or that I'm going to help you develop in this video, are all just taking into consideration their position along the string of LEDs, not yet taking into consideration their position in actual XYZ space. That will be the topic of the next video in this mini series. All right. And last in this mini series, I will probably have another video where I will take all the examples that we've done here and I will actually show you how they work on the physical tree. All right. I just want to remind everyone that we're doing this because we were very inspired by the work of Matt Parker from Stand Up Maths and the work that he did last year, where he bought the tree, he wrapped it with the LED lights, he created a computer vision routine where he was able to take snapshots and calibrate where these LEDs were in three-dimensional space. We're leaving off a lot of his work, his ideas, and some of the code that he published. And I would also like to thank my students who helped me put together the actual tree and wire the lights and do a lot of the code base especially for the calibration that we will be seeing in further videos. All right. So big hands up. Big kudos to Matt Parker and to my students. And I will probably post a link to this video somewhere popping up as a card here on the corner. And there will also be a link somewhere on the description of this video. All right. Okay, so let's start writing down like a few LED sequences. This is going to be a lot of fun. Ho ho ho! Okay, so let's get started. If you remember from the previous video in this mini series, which maybe the link is coming up as a card here on the corner, or is also in the description of this video. If you remember from the previous video, what we did there was, first of all, we were able to load the coordinates of a string of LED lights that was wrapped inside of around a Christmas tree, and how we had calibrated that and all the stuff. You can see Matt's video for that. But basically, we had generated the coordinates that we could load them from a CSV file so that we could see in three-dimensional space, we could see a representation of those LED lights. So that part is here. This was where we were loading those coordinates and created a family of points. And then in the previous video, we were also able to load from a CSV file, a different one. We were able to load a sequence of how those LED lights needed to turn on over the course of a certain amount of frames in a simulation of an animation, for example. We were able to load this CSV file, which looks something like this. We're going to take a look at that into a second. And then we wrote this custom script that was able to go through all those frames at a particular interval and connect it to this custom rendering pipeline with particular colors and particular meshes, so that at the end of the day, the result was that we could press play here and we could see an animation of what that light sequence looks like for all the points, all the LED lights on the tree that were represented as tiny spheres. In particular, this CSV file, this sequence had been designed to take a look at where those points are in three-dimensional space and create this animation of a plane that at any particular instance. All right. Now, this, in the previous video, we broke down how to simulate this whole environment, but we assumed two things. First of all, we assumed that we had a file with the coordinates of the LEDs. And again, I'm not going to get into that in this series of videos because that is like a little more complicated than I would like to. Anyway, and we still haven't figured out the process very cleanly yet. But it also assumes that you have this other CSV file that represents how all those LED lights get illuminated over a sequence of steps, in this case, we're going to call those frames. So what that looks like is something like this. So I have in my project file, I have the coordinates of the tree, and I have this moving plane CSV file, which is the one that has pre-recorded this motion, this animation of the lights turning on as the plane virtually travels the Z direction. What that looks like is something like this. The CSV has a particular format, and this is a particular format that me and my students designed so that exchanging these animations between different trees was a little easier. And the way this CSV is formatted is in the following. It has the first column that tells us what is the ID of the frame, and it's basically a bunch of consecutive numbers from 0 to whatever frame number it is. And then for every LED light, we have 3 columns representing the RGB colors of that LED light for every frame. So these are the 3 columns for LED 0. These are the 3 columns for LED 1, LED 2, each one of them being the RGB colors. So you can see, and there's 3 columns for every light. So you can see if I scroll all the way to the end, the last 3 columns are for the light 499, which means that this simulation contains data for. If we were to look at this simulation, we can see that clearly during the first 20 frames, there's nothing happening for the LED 0, 1, or 2. You can see that nothing is happening, but then during frame 21, you can see that LED 0 gets values of 23 for each one of the channels, and then it increases, and then it increases all the way to 244, and then it decreases down all the way to 0 in frame 39. And then from there on, it is 0 until the end of the simulation. What that means is that if the simulation takes 150 frames, this LED 0, is going to go from absolutely dark, is going to go to very, very bright, and then after that is going to decrease all the way to 0. And it looks like LED 1 has a very similar pattern, and then LED 2 has also a similar pattern, and LED 3, etc., etc. What this tells us is that every LED, as soon as it's time on the simulation, depending on where it is in the Z height, whenever it's its turn, then it will turn on a little bit and then it will turn off. All right? This is how we can encode these pre-recorded animations into CSV files and then can be replayed on the system that we have attached to the tree. But because this is a CSV file, I am opening it with Excel spreadsheet, which gives me like a very clean and nice tabular view of it. But I just want to remind you that CSV files are basically text files that contain values separated with commas. So if I were to open that file, that same file, inside of a text editor like Visual Studio Code, for example, you could see that it's basically rows of zeros, 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 and then rows of values. It's just the same kind of view. It's just that in Excel spreadsheet, the columns are a bit more aligned. It's a bit nicer to read, okay? So if what we want is to create a pre-recorded animation that then we can play on the tree, then in this particular case, in parametric cam, the example that we are doing is relying on the fact that someone has the capacity to generate a CSV file that contains this kind of code. So the first column is the ID of the frame, and then after that is just triplets of RGB values for each one of the LEDs. If you're able to conceptualize an animation and then dump or create a set of numerical representations that represents the state of the light at every frame, then we will be able to replay this and in the tree that we have, because the tree that we have is ready to take this kind of information and play it at a certain frame rate. Okay? So designing animations boils down to conceptualizing what we want to do and then be able to translate that conceptualization into a stepwise, frame-wise list of what all the colors of each one of the LED lights should be at any particular instance of time. All right, that's the general idea. So what does that look like in Grasshopper world? Well, in Grasshopper world, let's also full disclaimer, Grasshopper may not be the best tool for doing this because Grasshopper is not great at animations or dynamic things. And also, but Grasshopper is perhaps shines a bit more if we do animations that are specifically taking into consideration the spatiality of this, all right? But so maybe Grasshopper could arguably not be the best tool for this, but since we already did it here, and so we're just going to go for it. So what we're going to try to do then is we're going to try to build on the example that we did before, where we had the point coordinates and the simulation part, but instead of loading the sequence from a file that already exists, in this case, what we're going to try to do is we're going to try to generate the file ourselves so that we can save it in a file that we can load on the tree afterwards. But at the same time, we can link that file to the simulation pipeline that we have here so that we can simulate these things as we are designing them. So what is that going to look like? Well, first of all, I'm going to remove the loading part and I'm going to keep this simulation part here, and then I'm going to generate my first C# script component where I'm going to create my first CSV sequence. All right. And what is that going to be for a sequence? So I don't know. Well, you can't see the lights anymore, but we're going to start super simple. We're going to start with a simple sequence that what it does is it doesn't look at where the LED is. It doesn't look at, it's just going to turn all the LEDs on very slowly and off very slowly. On very slowly and off very slowly. We're going to call that a pulsing animation because it's going to feel like on, off, on, off. And all the lights are going to do it at the exact same time so that it's a bit easier for us to start warming up. All right. So let's take a look at how we're going to do that. I'm going to start by creating a C# component that I did here already. And I'm going to say that I want the output to be a CSV file, and then I will take care of saving that to somewhere on the file system at some point or whatever. And then the first input that I'm going to do is I would like to take the LEDs as an input. All right, and these LEDs designed before because there's a lot of information that we can get from that. These are going to be of the type which you can't see here because it's going on my other screen, are going to be of the type point3D. And then I'm going to ask for list access because I would like to be able to see all the points at once. So in the first sequence, it's going to be super easy, and we're actually going to have to deal with others. We're going to first start to deal with other stuff here. So, okay. So we're going to start by designing what is the algorithm. And first of all, what we're going to do is we're going to prepare the basics of our CSV file. The basics is that, if you remember, the file, the first line, what we're going to do is we're going to create a file as a sequence of lines. And each one of those lines is going to be a long string that we're going to generate. So the first line is going to be a long string that is going to contain all this stuff here. All this stuff here is, first of all, is the ID of the frame. And then after that is going to be triplets of this RGB plus the number of the LED that we're targeting. We don't really need this very strongly, but it's good to remain consistent, and it's a good exercise to do. So first of all, we're going to create the CSV file, and the CSV file is going to be a list of strings. Each one of the strings is going to be one of the lines. So for example, I'm going to call this rows, and that's going to be a new, or I can call this CSV, for example, and that's going to be a new list of string objects, right? But if I do that, then I'm going to have a clash with this name. So then I'm going to maybe just uppercase this. Okay. So CSV uppercase is going to be the output, and CSV is going to be the list of strings. All right. And then I'm going to add the header. The header, as we said, looks something like this. It starts with the ID of the frame, and then it starts with a sequence of 500 triplets of RGB and the name and the number of the LED. So what does that look like? So first of all, how many lights do we have? In this case, we can do LED count. It's going to be equal to LEDs dot count. However many are coming from the input. All right. So, all right, that's working good. What is the next thing that we want to do? We're going to add the header. The header, as we said, I'm just going to copy this. It's going to looking like, and then I'm going to copy this here. All right. Okay. So what that means is I'm going to create a variable that I'm going to call a row. All right. And I'm going to initialize that to frame.id and then a comma. All right. So now I have the first part of this, and then I will continue the rest, but so that we start getting some outputs. So let me say csv.add. I'm going to add this row, and then the outputs, so that I start building already something that I can see, is going to be that CSV file. I can now connect the panel here, and you can see that I have the very, very beginning of my CSV file. All right. Is that looking good? That looks good to me. What is the next thing that I would like to do? The next thing is I need to iterate 500 times or however many LED lights I have and add this sequence to the row. All right. So what I'm going to do is I'm going to iterate I equals 0, I is less than LED count, I plus plus, and then what I need to do is to the value of row, I'm going to need to add the following. I'm going to need to add first of all, r underscore plus the value of I, then comma, then rg underscore and the value of I plus, and then comma, b underscore and the value of I. Okay. If I do that, let me see if this works. I'm going to run this and you can see that it's kind of working, but I am missing the last comma here. All right. So I could do that. I could just add here the last comma, but that's not going to be great because I don't want to add that last comma unless we are in a row that is not the last one, because I don't want to end. So if you look here, if I go to the end of the CSV, you can see that the last column doesn't have a comma at the end. So what I would like to do then, I would like to say if I is any different from LED count minus 1, so if I is different than 499, then add the comma. Otherwise, don't do it. So what I'm going to do is row, and then I'm going to add the comma now, if this is the case. All right. And I'm going to add the commas there. And then it looks like RGB, RGB, it looks great. And if I scroll the way down, there is no, oh, you can't see that with my head. There is no trailing comma here. All right. So it looks like that is doing what we want. All right. Okay, so we have the header. So we are good. Now, what is the next thing that we need to do? We need to add for each frame, we need to add a row with the LED intensity for each one, for each LED. Before we actually start designing any animations or anything, we need to figure something out. And we need to figure out how many frames does our animation have. So that will depend on many things, but it will depend mostly on, first of all, how long do we want our animation to be? Do we want it to be 5 seconds, 10 seconds, an hour, whatever that is, right? And then we will also need to decide how dense that animation is. So how many frames, how many changes in the color of the lights we want for each second. Think about video. It's the exact same concept. We need to decide how many images per second we want to shove inside of one second. And then if the video has 30 frames per second and it's 10 seconds long, then all the images together will be 300 images, right? So same idea here. In order to do that, I'm going to add two parameters here. One of them is going to be FPS, which is going to stand for how many frames per second we want this animation to be. And the other one is going to be the duration in seconds. All right. So FPS is going to be an integer and duration is going to be also an integer. And then I probably want, for example, here, I probably want an animation that is about 60 frames per second. I was trying that on the tree and it worked pretty well. And then I want another that is going to be, the duration is going to be, for example, 10 seconds. All right. Then it's going to be very easy to just say, to figure out then, calculate total length of animation, integer frame count. It's going to be equal to FPS times the duration. So if we want 10 seconds at 60 frames per second, then we will have 600 frames. All right. And then we're not going to get, so I'm going to make like a fake CSV, which is going to be, I'm basically going to create empty rows for I'm going to create empty rows for all the LED lights, okay? So that we can have like a skeleton of what this looks like, and then after that we can start modifying the skeleton to add more or less things. So what I'm going to do then is I'm going to create, first of all, an animation that is absolutely nothing. Okay, so all the LEDs are always black, but I just want to try and see if I can get through all the process together. But then I'm going to do design rows, generate rows for each frame. So what I'm going to do here then is I'm going to say for int f is going to be 0, f is going to be less than frame count, and then f plus plus. Then this is going to be the amount of frames, okay? And for each frame, I'm going to create a new row. So I'm going to say, well, what I'm going to do is I'm going to reuse the variable that I had here, that I created row, and I'm going to initialize it to the frame count. So that's going to be f, all right? And then I'm going to add a comma here, all right? Then here I would calculate the values for each LED, all right, fine. And then whenever that happens, and then after that, add this row to the CSV. So what I would like to do then is I would like to say CSV dot. This thing that I just did should give me now a CSV file. I'm going to turn off wrapping, and so that you can see that the CSV now has the full length, etc. But then each one of the rows now starts properly. It starts with the name of the frame, and I get basically 600 frames because I was working at 60 frames per second for 10 seconds. Okay, that sounds about right. Okay, so then how do I then add all the RGB values for each one of the LED lights? Well, the way I can do that is here. And again, I'm going to start by just turning them all off. Okay, so nothing fancy about that. So what I'm going to do now is I'm going to create a for loop where I'm going to iterate over I equals 0, I is less than the amount of LEDs, so LED count, is that correct? LED count, and then I plus plus. All right. And then what I would like to do here is I'm going to declare outside of the for loop, I'm going to declare 3 variables, int r, that I'm going to initialize to 0, g, that I'm going to initialize to 0, and then b, that I'm also going to initialize to 0. And I'm going to be reusing those variables to calculate things once I'm ready for calculations, okay? But then in the meantime, because they're all going to be 0, what I'm going to do is that for each LED to the row, I'm going to add the values of those 3 RGB colors. Again, I'm not going to here, at some point, I would calculate values, RGB values for each, I will calculate each value for each LED, right? And actually, why don't we just do this? So I'm actually going to do R, A, R, G, and B. We're also going to calculate alpha, okay? And then here, alpha is going to be fully opaque, so that's 255. Then R is going to be 0 for this LED light, G is going to be 0, and B is also going to be 0. Okay. For this one, all LEDs are black. Okay. And then what I would like to do now is I would like to say for this color, the row, actually, I don't really need the alpha we did for the simulation, but we don't need to generate it here. So RGB is going to be 0. And then what I do here is add these colors to the row. So I do row is going to be equal to the value of R plus a comma plus the value of G plus a comma plus the value of B plus a comma. Oh, sorry, the value of B. And then if I is different from LED count, then to the value of row, I'm going to add this last comma, okay? So that for the very, very last element, I don't have that. Beautiful. So let me run this and you can see that it looks like this is working. All right, so I have zeros all through. All right. And this was not very exciting, but at least we got the basics covered. All right. The basics covered, because now what I would like to do now is I would like to write this to, I would like to write this CSV file to somewhere on my system so that I could send this to, the Christmas tree. As far as I know, Grasshopper doesn't really have a component to save to the file system, or I'm missing that. I'm not really sure, but we can write this on our own. So I'm going to create a new C# script, all right? And then this is going to be the CSV that we want to write. And then this is going to be the path in my system where I want to send this to. The CSV is going to be a list of strings, all right? So that's going to be of the type list, and this is going to be a list of strings, which is exactly what I'm getting out of here. And then the path is going to be a simple string, all right? Where am I going to save this? So for example, I believe that right now my workings folder looks something like this. So for example, I'm going to write this here, desktop, Christmas tree, etc. And the file name is going to be, for example, allblack.csv. All right. Allblack.csv. Beautiful. If I do this, if I do this and I connect this here, and I don't really need an output because this is going to be the output of, okay. And then what I can do here is I'm going to say, first of all, I need to write my CSV to somewhere on my file system. The namespaces in C# that we use for writing to and reading from the file system are this. So that's going to be system.io, and then using system.text. All right. So what are we going to do here? What I'm going to do is I'm going to say file.write all lines. This is going to take a string as a path. So that's going to be the path. And then the content is going to be the CSV that I want to save. All right. And then I have something additional, which is that I can also add which encoding do I want to use. This is useful because depending on which system do you work with, if you rely on your default encoding, the files may not be compatible between different systems. So it's always useful to stick to a default, an encoding that you know. And so for example, I'm going to choose here encoding.utf8. I could choose ASCII, but UTF-8 is pretty much the one that is taking over, all right? So if I do that, then let me see if this is going to work. I'm going to dock this here, and I have my file system. I have this. So if I run this, I can see that I have now this new CSV file called allblack. If I turn it on, if I load it, you can see that I have the 600 rows and that all the pixels, every channel for every pixel is purely black. If I load this, I don't know where I am. Yes, if I load this on my Visual Studio Code, you can see that everything is just zeros. It's a very boring sequence, okay? But at least it works. So we have the CSV generation part figured out. And then I'm going to minimize this. So this is figured out. Now, a few things that I want to do, writing and reading from the file system, that can be tricky and can be very faulty, because if the file is busy with some other some other process is looking at the file, it's locked, whatever, you may not be able to overwrite it. So it's very typical to wrap things that involve file system manipulations, wrap them into try catch clauses, all right, so that if it fails, it gives us some warning. So I'm going to wrap this as a catch. I'm going to say I want to read an exception, and then component dot add time this. So this component, I'm going to add a runtime warning, and then grasshopper runtime message level dot is going to be an error. And this is going to be, I'm going to add here, could not save file error. And then the error is going to be whatever we got from the exception. All right, so that's a very typical thing. Otherwise, I'm going to print to the output, file successfully saved. All right. And maybe just for the sake of it, for example, we can add date time. Do we have date time? Dot now. Yes. Okay. Beautiful. If we do that, and if we plug here a panel, you can see that, yeah, this was fully successfully saved on the 24th of November 2021. That's when I'm recording this at 3:21 my time. And if I recompute everything, you can see that this got saved again and the date updated. So it's a good feedback to see. All right. Beautiful. Okay, so we have now a system to generate the most boring light illumination on Earth. We can save it to our file system, and we can also now plug this CSV into what we did before, into the simulation, and run this simulation. So for example, I'm going to turn off the LED, the cross. I'm going to run this, and you can see that I'm going to reset this. Input string was not in the correct format. I don't know what that means, or oh wait, so maybe this was expecting the CSV file to not have a header, correct? Maybe that's the case. So I may need to modify this and remove the header from here and plug this in here. I believe that was the problem. Yes. So yes, so this simulation expect to not have the header. So we could actually save ourselves the header, honestly. Save ourselves the header and the headache. Okay, but it's working, it's animating. We see nothing because there's really nothing happening here. But it's working, okay. Beautiful. So how can we now start generating sequences that make any sense whatsoever? All right. Let's start simple. Okay, I was going to do the pulsing light as the first example, but for the sake of effect and impact, why don't we just do something real quick? Why don't we try to just generate absolute random blinking all through the simulation? I think that could be a quick one to do. So I'm going to group this, all right? And then I'm going to remove this. So this is the first generation, which is basically all black. And we're going to call this flush, because flush is one that we can use to, we will see very soon, we can use this one to basically clear out previous, so I'm going to call this flush, all right? And that's going to mean to remove whatever lights were left over from a previous sequence, all right? Then the next one, I'm going to copy and paste the whole thing, and I'm going to call this complete random blinking, all right? What that means is here, random blinking, all right? That's going to be the name of the CSV file. Random blinking is going to be that at any frame, what I'm going to do is I'm going to calculate a random value between 0 and 55, and I'm going to turn each LED with that random color, with that random color. So for example, what I'm going to do here is I'm going to say, I'm going to calculate the values for each LED light. First of all, here I'm going to create a random object generator, and I'm going to say random RND is going to be a new random object. All right. Is this going to work? Yes. Now, before I calculate the values for each LED light, what I'm going to do is here, I'm going to calculate a random value between 0 and 1, and between 0 and 255. So here, what I'm going to do is, I'm going to calculate random is going to be the following. I'm going to take the random object, and I'm going to get the next double. No, sorry, I'm going to get the next, which gives me an integer already. So that's great. Integer, and the minimum value is going to be 0, and the maximum value is going to be 255, 256. Because it turns out that if you look at the specification of the random number generator in C#, random numbers between two domains can have the value of the minimum boundary, but they will never have the value of the top boundary. So if we want an equal distribution that actually sometimes yield the value of 255, then the maximum value needs to be 256, which is guaranteed to never be produced by the random number generator. Okay, so for all the LEDs, I'm going to generate the same random number. And I'm going to use that same random number as the RGB value. What that's going to mean is that if I do that, look at what happens in the CSV file. Every triplet got the same value, and all the LED lights have the exact same value. What that means is that every frame, the whole tree is going to get a random gray or a random value of the light, but all the LEDs are going to be the same. And then for the next frame, it's going to change, it's going to change, it's going to change. Let's take a look at how that looks like from a simulation standpoint. I'm going to plug this in here. I'm going to reset, and then something is not working. Something is not working. Let me see what is going on. Let me take a look. All right. It was the silliest mistake. So I plugged in the output of the CSV saver, the thing that saves the file, where actually I should have plugged in the output of the actual CSV component. So yes, so this is here, and then you can see the whole tree is flashing. All right, so that is not great. So I mean, we could illuminate the tree like this, but it's just not nice. So I'm going to stop it, because I don't like that at all. So what I would like to do then is just get every blinky, every LED light, its own randomness. So what I'm going to do here then is, for inside of the for loop where we iterate over all the LED lights, so I'm going to do is, I'm going to calculate a new random number for each LED. And then I'm going to make all the RGBs equal to this random number, so that we have a scale of grace. All right. And I see Indrajit on the chat. Welcome, Indrajit. Indrajit has been the mastermind who has helped me put together this exercise. So the tree, and to build the tree, and to write the code, to run the calibration, etc. Thank you very much, Indrajit, for all your work. Now, as I was saying, now if we move this random into the for loop that we use to iterate over each LED light, then one different random value will be generated for each LED light. And then we can assign that same number to the 3 coordinates, RGB, so that we get a value of gray. And then you can see that already we got something much nicer. So you can see the triplets, 210, 32, 104, and then next frame, blah, 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 whatever. And if we simulate this now, you can see that, well, it's also a Caesar, but it's not so terrible, you know, but it's like a random blinky of some kind. Okay. Beautiful. So how can we write a version of this that, instead of being a grayscale, also blinks with different colors? Of course we can. And then what we're going to do is we're just going to copy and paste the whole thing, and then random blinking with color. And then I'm going to save this random blinking, and then I'm going to add here a hyphen color. All right. And then here it's just going to be as simple as saying, well, we generated a random value, and then we use the same random value for RGB. So this, if we want colors, then the only thing that we need to do is that it's going to be as easy as saying, well, each time we generate the green, the ground, the red or the blue, we want a different random value for each one of the channels. If we do this, it's going to be complete chaos, but you can see that now each one of the values of the RGB is like all over the place. If we plug this into the simulation, then you can see that I now have like random colors, and then this is going to be, I don't know how I feel about this. I really don't like this kind of effects. I'm much more of a minimalist here. So, but as a baseline, we already got something going on, and this in the tree will definitely look very flashy. Not sure that I'm happy with it, but it will be whatever, okay? So, can we now go back to the basics and create a sequence that is a bit more elegant? Okay, let's do that. So now let's try to break down how to create a simple simulation where all the LED lights pulse, like they go on and off, but in a very smooth transitional way, all right? Which I feel is going to be much more Christmassy. But before we do that, we're going to have to, I would like to break down the logic a little bit on the whiteboard. Let's take a look at that. The way I would like for us to think about this problem is the problem of discretizing time and thinking of an animation that evolves over time, how we can chop that full continuous animation into units of time that in our case are going to be frames, and then how can we calculate the values of illumination for each one of those LED values based on where we are along that time span that we're targeting. So from a numerical standpoint, this could look something like this. For example, imagine we look at every single LED light. And for every LED light, we know that the range of values that it can get is somewhere from 0 to 255. So we know, and we're doing monochrome for the time being. We will get into RGB later on. So if we think monochrome from black to white, then the range of values that it can get is from 0 to 255. Since we want to create an animation that starts from black and then it pulses into full brightness and then it pulses back into black, then if we think of this over time, what we would like to do is for our illumination value or brightness value to start somewhere here, right? And do something like this, like slowly accelerate over to 255, decelerate, and then go back to the value of 0, more or less, all right? If we were to look at that exact same animation, but we were to plot it in 2D by saying, let me create a graphic where one axis is going to be brightness, the same one, the vertical one, but the other one is going to be time. If I think of my animation, what I want to create is something like this. I want to start at the very beginning of my animation with the value of 0. Then I want my animation over time, over half the time, to get to the maximum value, in this case 255, and then symmetrically, by the end of my simulation, I would like it to go back to the value of 0 again. That is actually possible if we start thinking of time as something that we can discretize in individual units. And because we know how much time we want our animation to last, 10 seconds, 15 seconds, an hour, whatever that is. And then we also know how many frames we're going to be rendered in this by second, 30, 60, whatever that is. Then it's very easy to calculate how many frames altogether our animation should have, each one of these tiny bars. And then it will be just a matter of finding a numerical rule so that for each one of these units of time, the frames, we find what the corresponding value on that curve is going to be. All right, so for each time of the frames, we calculate what the value of the brightness should be at that particular instance of time. For this particular example, because it's going to be a super simple start from black, go to maximum and then smooth back again, you can see how I'm probably going to be using a sine wave because because the sine function is a function that for any particular value between 0 and 2 pi or tau, for any particular value, we know that that function oscillates between the values of 0 to 1 to 0 to -1. All right. So let's start by building the prototype with the sine function, and then let's see what we will need to do to tweak that so that it looks exactly like this. All right, let's take a look at that. Back in my grasshopper definition, I have gone ahead and copied the flush, so the pure black animation. I copy pasted it here, and now I'm calling it pulse uniform. All right, and then I'm going to go into the code here. We have the algorithm, we prepare the header, the length of the animation, etc. We generate the rows, we calculate the values for each LED, and then here we calculate the values for each LED. All right, beautiful. So for this one, what we're going to do is, if you remember, we said we need to divide time in the amount of frames. We've already done that. We know how many frames. All right, we need to calculate 4, but then because we want to go from minimum to maximum and to minimum, and we're going to be using the sine function, what I would like to do is, because the sine function goes a full cycle from 0 to 2 pi or tau, what I would like to do is I would like to calculate what is the increment of the angle that I need for the sine function in order that matches the amount of subdivisions that I have in my timeline. What that means is that if a full cycle is tau or 2 pi and I have 600 frames, I need to divide tau by 600 frames to know what is the increment of in the cycle that I need for each one of my frames. All right, so what that looks like is I'm going to calculate here angle, no, I want to angle step for each frame. So I'm going to call this value, for example, I'm going to call it theta. All right, and that's going to be theta step, because we have, what I want to do is 2 math pi divided by the total amount of frames, so frame count. All right, and this is not going to be an integer, this is going to be a double. Beautiful. What that means then is that for the values of the LEDs here for this frame, I'm going to calculate the value of theta. So the value of the angle for the sine function that I'm going to be using, the value of the angle for the sine function that corresponds to this particular frame. And because I have the step, so the only thing that I need to do is I need to multiply that step by the amount of frames that have elapsed. So that's going to be f. All right. Let me just print this so that we understand what this is coming for. So theta, so I'm going to say frame f plus, and then here a theta of whatever that is. Let me print that to the console. All right, and so that we can see this, I'm going to plug this in here. So you can see each frame has an associated value of theta from 0 to tau, which is roughly 6.28. All right, that's going to give me a full cycle from 0 to 2 pi. Now I'm going to say, well, what I would like to do now is I would like here to calculate for this theta, what is the sine of that what is the sine of that value. So I'm going to calculate the amplitude. I'm going to call it, for example, And then I'm going to say that that is going to be the sine of theta, for example. And that's going to give me a value between -1 and 1. So for example, and then I'm going to go here, amplitude is going to be equal to amplitude. All right, I'm going to print that to the console, and now you can see that this is going to give me a value that starts with 0, is going to go all the way to 1 somewhere by the middle of the simulation. So that's going to be 150. And then it's going to go back all the way to 0 at the middle, at the center of the simulation. So that's going to be here. This is 0, it's just a number with a very small decimal. And then at 450, I can probably expect -1, right? -1. And then all the way at the end, I can expect back to 0. So this is looking good. It's not exactly from 2 to 55, but we will work with that in a second, okay? So what I'm going to do now is, because I have amplitude, what I can do is I can say, well, I'm going to do amplitude times 255 times the amplitude. All right? That's going to give me values between, all right? And then you can see that I cannot convert explicitly to an integer, so I need to convert this to an integer. All right, so this calculation needs to be casted to an integer. All right, and that is still not an explicit conversion. Okay, so maybe I need to round it. Math.round, and then I need to round this thing here. And then I'm going to, I could do the same thing, right? So this is going to work. And then you can see how the values for the CSV start at 0, 3, blah, blah, blah. They increment all the way to 255 on frame 150, which is kind of nice. And then at frames 300, they're probably going to drop to 0. Right? And then I start getting negative values, which I will deal with later, because we can't have negative values here. So if I animate this now, this is going to look, you see, it's pulsing, it's becoming blah, it's becoming white, and at 150 it's going to max out. It maxed out, and then it's probably going to go dimmer. It's going to go dimmer. And then we are now at negative, okay? And because we're at negative, it fails, because look at we get. Value of -3 is not valid for a red channel, okay? All right. So what can we do about this? So what you can see is that what I've generated right now is something that, because I'm using the sine wave goes from 0 to basically the value of 1, then the value of -1, and then the value of 0. Okay, which is not what I wanted. So what I wanted, first of all, is to go from 0 to 255, and that's why I multiplied it by 255, but it turns out that I also get this area here, which is all negative values, and that's probably not what I want. Okay, so what can I do? It feels like something that would be interesting is to take this whole curve and somehow squish it so that it could fit here, right? And I could have a perfect cycle, correct? So that would be great. And that would be great. So how can I do that? Well, I'm going to do some very simple numerical rule. And if I right now have a curve that looks something like this, if I want to squish it by half, the only thing that I need to do is I need to multiply the value of the sine by 0.5. And then if I want to take this curve and move it up, the only thing like this, offset it, the only thing that I need to do is I need to add another 0.5 to that value, to the result. So let me show you what that looks like. So I'm going to say, where am I? Ooh, not here. What I'm going to do is I'm going to say here, for the value of the brightness, okay? The value of the brightness that I had was this thing here, correct? That's the value of the brightness that I had. And this was brightness, and then this was brightness, and this was brightness, all right? So this was what I had. So because I have the amplitude here, what I want to do is I want to multiply this whole thing by 0.5. If I multiply this whole thing by 0.5, then you can see that now the value of the amplitude here is going from 0 all the way to 0.5 at 150, which is, you see, at 150, which is a quarter of the simulation. Then it's going back to 0 at 300. Where are we? 0 at 300, and then negative, and then positive. So we have squished the whole thing. We have squished it by half. And now what I want to do is I want to move the curve, or the whole thing, up in the positive direction by a value of 0.5. So the only thing that I need to do is to this, I will need to add now here to the amplitude, I will need to add another 0.5 plus the resulting value of this theta. If I do this, then you can see that now the value of the sine is going to start at 0.5, is going to go all the way to 1, then it's going to go all the way back to 0.5, and then it's going to min at at 150, at 450 is going to become 0, and then it's going to go all the way back to 0.5. Okay, so if I run this now, you can see that if I reset, now I can run this, and it starts at half gray, and then it goes all the way up to maximum at 0.55, and then it's slowing, going down. It's going down very fast to 0. And then you see how it slows down? It's slowing down at 0, and then it goes back up to 0.5. All right, beautiful. The last thing that I may, just because I have OCD, the last thing I would like to do perhaps is, you see how the result of this is that we start the simulation at 0.5 at half brightness. So if we start at half brightness, then then it's not really nice. So what I would like to do is, I would like to start here with the value of 0. So the only thing that I need to do is I need to move the whole curve, the whole sine curve, a value of half pi or a quarter tau, so that I need to offset it by this distance, so that the curve starts here, goes here up, and then does this. All right. How can I do that? Well, that's going to be super easy. Here, when I was doing the calculation for the sine wave in the amplitude, then it's just as simple as adding to the value of theta a value of a quarter tau, or in this case, half pi. So to theta, I'm going to offset, whatever it is, I'm going to offset it by 0.5 times math.pi. And if I do that, you can see that the very, very beginning is 255 up. So I actually missed the sign. It turns out that it's negative. I need to offset it by minus 0.5 math pi. And now the simulation starts at 0. And then the whole thing pulses. All right. Oh, sorry, you didn't see any of that. Oh, sorry. Sorry, I did that with the wrong. So this is here. So what I did was, here where I'm calculating the amplitude, I added to theta, I added a negative 0.5 math pi, or a quarter of the full cycle of the sine wave. Okay. And that's it. That is a pulsing animation of the whole tree, all the LED lights pulsing at the exact same time. How does that look like? Huh? It's getting exciting, huh? So, but you know where we're going with this now, right? We are going to now try to see if we can make each one of the LED lights pulse at its own pace, at a different, not amplitude, yes, at a different, with a different offset. Let's give that a try. What I have done for this one is I have copy pasted the pulse uniform. I have copied it here, and I'm going to call this pulse random. All right. And what this is going to be is just that. Let's take a look at the whiteboard first. If we follow the same logic we were following before, then when we were thinking about the curve and how we were moving it, we can see how what we chose for our animation is that all the LEDs started here at 0 and they all followed the same curve at the exact same pace. But if you think about how, if we want each one of them to have their own cycle, then it probably is just as easy as deciding that each one of the LED lights is going to start at a random value. So for example, one of them may start at 0, another one may start at 100, another one may start at 200, and then each one of them over time is going to change at the exact same rate. But because they started with an offsetting value, this will lead to this one, for example, reaching maximum earlier and then ending here, but then ending at a similar value. And this one here may reach this super early, and then this one here may reach this value like this, you know. The drawing is not great, but another one here may do something like this, you know. So you see where I'm going with this. It's going to be just as simple as deciding for each LED light, having an initial value of the offset of the angle that we're using for calculating the sine value, and then using that as a way of having each one of them maintain its own cycle. All right, let's take a look at what that looks like. So this is going to be something like this. So we're going to say, before we start creating anything, I'm going to generate random initial angles for each LED light. The way we can do this is, for example, I'm going to create a list of doubles. So double initial theta, and that's going to be new list of blah, 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 and okay, and initial double. All right. And then where is it that I created the random? I don't have the random number generator on this one. Okay, so that's fine. So I can say random is going to be equal to a new random object. All right, beautiful. Now what I can do is I can say I'm going to iterate over all the LEDs, LED count, and then I++. And then here I'm going to say, I'm going to calculate a new random number, double random theta. Okay, and that's going to be equal to random, and then give me a next double, the next double. All right. What this does is that it generates a number that is random between 0 and 1. Because it's between 0 and 1, we want this value to be instead a random value between 0 and 2 and 250, and 2 pi, so that we start at a different place in the cycle of the sine wave. So what we need to do is we need to multiply this by 2 times math pi. As we do that, then this will be a random value between 0 and 2 pi that we can add to initial thetas. I'm going to add this random target, okay? And then what we need to do now is, now the calculation of the amplitude is not going to be the same for all the LEDs. It's going to be different for each one of the LEDs. So I'm going to have to take this and move this inside of and I'm going to move this inside of the for loop that is taking into consideration each one of the LEDs. And you can see that to this angle, to the angle theta, what I'm going to have to do is I'm going to need to also add that initial offset that I generated for each one of them. So I'm going to have to add init theta of I. Okay, so that is going to be the initial random angle with which each one of these each one of these LED lights started. Okay, beautiful. Okay, so if I do that, then I get something here, and then sorry, whatever I do, I'm going to plug this in here, and it looks like I'm getting something. So I got random initial values, and then if I press play, you can see how, I don't know if you can notice, but they are slightly changing. Let me change let me change this and make it shorter. Okay, so we're going to I'm not sure that this is changing actually. I'm not really sure that this is changing. Well, let's see here. We don't have to speculate. This one goes from 0, it goes to 0. And then this one is maxing out, and this one is going all the way up. So it is working, it's just that it's very painfully slow. Okay, but it is actually working. So maybe we can speed it up and we can say 30 frames per second. Oh, wait, so I changed the wrong one. Oh, yeah. Sorry. I changed the wrong one. That's 10, so 30 frames per second in 2 seconds. Okay, and then, alrighty. That's much better. Okay. So you can see how each one of them is pulsing at its own pace. All right. So let me put this back at 60 and put it back at 10. Yeah, it's just very slow. Nah. So we're going to do 5 seconds for this one. Okay. Or maybe even less, 3 seconds. Okay, we like 3 seconds for this one. So that the 3 pulses, yeah. Beautiful. Alrighty, so now we have lights pulsing at the same rate, at different rates. And what about if we actually have them pulse with a slight offset from each other? Okay, what does that mean? What I mean with a slight offset is that if instead of just randomly starting from whatever, and then getting like a curve here, another curve here, another curve here that looks kind of, if what I do is the initial values are actually all in sequence, and then because all the LED lights that go from 0 to 500, they're all actually very physically close to each other. If what I do is instead of giving them random values between them, what I do is that I give them random offsets that are very close to each other from one another. From a mathematical standpoint, what I would end up getting is a curve that looks like this, another curve that looks like this, another curve that looks like this. So I would get like a much more homogeneous distribution, if you will. But in the physical space, what I will end up getting is I would end up adding a sequence of blinking that kind of follows the trajectory of the LED cable that is wrapped around the tree. So this is just as simple as creating a sequence where the initial values are not random, but they are simply a slight offset from one to the other. What that looks like is, let me copy and paste this, and then I'm going to call this pulse with an offset, all right? And then this one is going to be called pulse with an offset. And then here, in the original, here, instead of creating these numbers with a random initial, with a slight offset initial angles, what I can do is I can say, I'm going to create a value here, but this value, instead of being random, what it's going to be is going to be starting from 0, and it's going to be the full cycle, so 2 pi divided by the amount of LEDs that I have, and then multiplied by where this LED is on the sequence of these LEDs. So that's going to look something like 2 times math pi divided by the amount of LEDs that I have. All right, so divided by LED count. So that would be how much angle in sine terms there is between each one of them, and then multiplied by the position of this LED inside of the sequence of LEDs. If I do that, just as simple as that, if I do that, what I'm going to get is a distribution that is going to look much more sensitive to where those LEDs are in three-dimensional space. So if you can see now, if I run this, because you can see that how all these LED lights, which are in sequence, they start turning on more in a gradual way, right? And then they go down the tree and vice versa, which is kind of super nice, right? And this is because, again, the position of these elements in three-dimensional space is based on a calibration routine that my students and I work together, and that is kind of working, and needs a little bit of polishing, but it's kind of there. So it gives a very nice spatial effect. All right. Beautiful. Can we add some color to all this stuff? The way we're going to add color is that I'm going to take the sequence that was a random pulse, so this one, and I'm going to duplicate it here. I'm going to be based off from this one. But what I would like to do now is I would like to maintain this random spirit of the pulsing. So I'm going to keep random, but then I'm going to divide all the LED lights in two groups. One that is going to be red lights and another one that is going to be green lights, because, you know, it's Christmas lights. So, and then each one of them is going to pulse at its own rate, but it's going to be rendered with a different color. So pulse random color, I'm going to save that here, all right? And then I'm going to get into the code. And what I would like to do here now is that just like I created a list with 500 numbers that represented the random offset that each one of these LEDs start with, what I would also like to do is I would like to create a list with 500 Boolean values, each one of them representing whether if the LED is going to be red and whether if it's going to be green, and then randomly assign values to the beginning of that. So I'm going to start generate random distribution of colors. So what's that going to look like? I'm going to create a list of Boolean values, and I'm going to call that is red. All right, that's going to be a new list of Boolean values. And then for each one of the LEDs, I'm going to copy this for loop here. For each one of the LEDs, what I'm going to do is I'm going to create a random number between 0 and 1. And if the value is 0, then is red is going to be true. And if the value is 1, it's going to be false. All right. So how am I going to do that? Well, I'm going to say integer, random integer is going to be equal to the random generator that I had, and a next value that is going to be from 0 to 2. And remember, I'm using 2 because I know it's guaranteed that the result will never be the maximum value. It can be the minimum value, but it will not be the maximum value. So if I want a 50% distribution between results 0 and results 1, then this has to be the value of 2. And then here, what I can say to the value of is red, I'm going to add, what am I going to add? Is this equal to 0? Then I'm going to add the value of false. Otherwise, I'm going to add the value of true. This is a ternary, I don't know how to pronounce that, ternary conditional. I believe I have a video somewhere explaining that, so there might be a card popping somewhere here or there if you're not familiar with this. Anyway, so with this, now I have a list of 500 booleans, trues or false, which I'm going to use to decide whether if the light should be red or blue. All right, here the calculations for the brightness are going to remain the same. I get a value of brightness, but then here, what I'm going to do is I'm going to say, choose red or green. So I'm going to say if is red for this LED light that I'm in right now. If this is true, then the values for R should be brightness, and then the value of green should be 0, and the value of blue should be 0. That's one thing. Otherwise, if I don't, then this, if it's red is not true, then brightness should be here and red should be here. Correct? Let's try that out. So I'm going to run this and I can see some values here. I'm going to plug this. Are you ready for this? Are you ready for this? What? Are you ready for this? And I'm gonna plug it here and woohoo! Why? No, what happened? Oh no, I have to plug it in here, sorry. Oh, oopsies. Okay, so I'm going to have to redo this. So it goes in here, and this is the one that goes here, and then etc. And then you can see that it's pulsing painfully slowly. Let me speed this up a little bit. So I'm going to do the value of 2, and then I'm going, okay. So you can see how now the tree is pulsing between reds, blacks, and greens. All right, it's very Christmassy. I kind of like it. I have to say though, I was running this yesterday in the in the tree, and my partner, who's a minimalist like me, she was like, "No, I don't know about this. We're gonna have to keep it in the white domain, huh?" Our Christmas tree is very minimal this year. Okay. All right, beautiful. What are we going to do next now? And I believe that at this point, the thing that we're going to do is we're going to move on to the next video, because I think this one has gotten pretty big at this point. And I kind of like that all the sequences that we did here were sequences that didn't really need, in a way, to know where the LEDs were in three-dimensional space. They were just playing with random values, with positions, with the sequence of where the LEDs are one after the other, but not in spatial terms. And I have a few other examples that I would like to run on that actually rely on knowing and playing with where the LEDs are in three-dimensional space. So I think I'm just going to move all of those examples to the next video. And I will also showcase those examples executed on the tree in the last video. All right. So, or maybe not, or maybe I just do one video just for that. Okay. Okay. So then I'm going to wrap up this video. Thank you very much for being there. Thank you very much for sitting down through this whole thing. I hope you found this exciting and fun. I'm dying to show you how these things look on the Christmas tree, okay? Which will happen very, very soon, all right? So in the meantime, if you thought this was cool or fun or whatever, you may wanna like this video, subscribe to the channel, leave a comment, join Discord, send us a coffee, I don't know, whatever that looks like for you, all right? So thank you very much, and see you in the next video, where I will do more examples that are actually aware of the location of these elements in three-dimensional space. Thank you. Bye-bye.